Welcome back, folks. So today we're going to take the next step in our experimenting around with operational amplifiers. And again, like with the other episodes in these series, it's sponsored by PCBWay. So we're going to look at an operational amplifier differentiator and the op-amp integrator. Now, you know, there's no equations here. I'll get to that in a second. But these are two very important circuits that operational amplifiers are used for. They do a variety of important things, and we won't look at that now. What we will do, though, is look at it in the next episode when we actually build these up and try them out. Now, we're going to be using the same boards as we had before, so I don't need to send off a new design to PCBWay for this. We're going to use the same boards as we had before in the previous episode. But I do have to wait for some operational amplifiers to get in because I kind of ran out of them. But so we'll be back. Part 2 will be coming up in a couple of weeks, I guess. So before we go too much further, though, let's go get a word from our sponsor, PCBWay. PCBWay is a fantastic place to go and get your prototype PC boards made up. They make it so simple, they do it so quickly, and they just do it with extremely high quality. But once your prototype has been designed and finalized and you want a custom case for it, where do you go for that? Well, PCBWay. They have complete sheet metal fabrication service. And they explain their process. They tell you what the capabilities are, what their sheet metal cutting types are. They even give you the advantages and disadvantages. And they have a vast array of fabrication processes, materials, surface finishes, colors, anodization, powder coating. So you need a special case built up. It's just as easy as it is getting PCB boards made to get a quote from them. All you have to do is put your CAD files in place, tell them how many they want. It'll decide the design units from the CAD files you put in, but you can also put all this stuff in manually. Select your materials, select your colors, and submit your information, and they'll come back to you with a quote for what it's going to cost. It's just that easy. Anything you do at PCBWay is done easily, it's done quickly, and it's done right. Give them a try. All right, we're back. And so let's go down here and derive how this particular circuit here, very simple circuit, it looks like the regular inverting amplifier circuit, except for you have a capacitor here instead of another resistor. And let's look at why and how this is a differentiator. So here you just put down some of our rules here. We know that the input current is going to be equal to the feedback current, which is the current through R1. And we know also that that feedback current is equal to minus VO over R1. We also know, or we should know, that the charge on a capacitor is given by its capacitance times its voltage. So in our case, the charge on C1 is going to be V in times C1. Now, I in, the input current, is equal to the rate of change of that charge. So the current flow going in is going to change the charge, and that is our current. So you write down dq by dt equals C1 times dV in by dt. And what I mean by dV in by dt is the rate of change. So this is the differential of the input voltage. So the differential of the charge is equal to C1 times the differential of the input voltage, which is our input current. And what we mean by derivative is the instantaneous rate of change. So the derivative of a function, in this case the input voltage, at a particular point in time is the derivative of the function at that point in time. And that's the job of the differentiator. So if we rearrange that, we get minus V out over R1 equals C1 times the rate of change of the input current. We can then rearrange that to get V out is equal to this constant, which is minus R1 times C1, all times the rate of change or the derivative of the input voltage. So our output is proportional to the derivative of our input voltage, and that's why this is a differentiator. And this gives us the ability to do real-time calculus with hardware. So let's move on now to the integrator. And you notice I don't have any equations here. That's because we're not going to use this. The reason we're not going to use this is that if you remember our little experimenter here, one side of the operational amplifier is inverting and the other is non-inverting. So while the standard op-amp integrator is also a inverting circuit, and you notice it's the very same as the differentiator, except the capacitor and resistor change places. But we can't use this. We need to find one that works on the non-inverting side. And lo and behold, there is one. So this is it. This is the op-amp integrator non-inverting. And in this case, we're going to need two resistors, the same value, and two capacitors, the same value, because the behavior at the positive input has to kind of match the behavior in the negative input. And in this case, we're going to look at these two different circuits and equate them. So essentially what we have here, the small v, we know how an operational amplifier works. Whatever we do with the negative feedback will cause the input at the positive terminal to be the same as the input voltage at the negative terminal. So we're equating these two small v's here. So if we look at the input current, the input current is V in minus V over R, which is equal to the capacitance times the derivative of this voltage here, how it changes over time. And the feedback current is equal to V over R, which is equal to C times the derivative of VO minus V with respect to time. Now we can just write that out. We can expand that out so that we get feedback current is equal to C times the derivative of V naught minus the derivative of V with respect to time. And the reason I got these two little green boxes over here is because this and this are the same. So we can substitute this in for this. So now we get this equation here. So we get VR in terms of the rate of change of V out minus the rate of change of V in minus V over R. We can rewrite all that. So we just expand this term out here. And then we notice that we have these two on either side. We can eliminate them. And it simplifies down to this. After a little bit of rearrangement, we get a C times the derivative of output voltage is equal to Vn over R. So now we just write that out in the standard differential form, and then integrate both sides. We get V out is equal to this constant 1 over RC times the integral of V in. So we can see that our voltage output is proportional to the integral of our V in, and that gives us our op-amp integrator. So now that we have the function of an integrator and the function of a differentiator, we essentially have the whole of calculus. So that in hardware we can put in extremely powerful mathematical terms. We can solve differential equations on the fly. We can determine rates of change and do anything you can do with a pen and a piece of paper built into our hardware, and it's real time. That's how significant these circuits are. So using this circuit along with this circuit will allow us to put both a differentiator and an integrator onto our little experimenter here. That's really all I had to go through with you today. Now, I know probably most of this math is a little bit beyond most beginners, so if you have any questions about it at all, please ask in the comments. And other than that, we'll come back in a couple of weeks. We'll build these up, and we'll show you what they can do. Quite interesting. All right, folks, thanks for joining me today. We'll see you in the next video, and in the meantime, do some electronics. Bye-bye.